So, the aim of this lecture is to give an idea of the linearization procedure which is used in continuum mechanics. The reason for which this procedure is performed, the reason for which people decided to use this kind of procedure in continuum mechanics is clear. When you have non-linear equations, the methods needed for solving them are more complicated. Moreover, linear equations usually have a reasonable behavior. The solution under reasonable conditions exists and is unique. While non-linear equations, as it has to be, because in general, in nature, there is not always a unique solution to every problem. There is not a unique evolution for every problem. Non-linearities are were studied only very recently, and it was even trendy to consider them. Many departments changed their name into non-linear analysis, non-linear mechanics. Many journals are called non-linear, which is very strange because always the equations were written in a non-linear way. Piola wrote divergence of this animal plus external bulk forces pushed back on the Lagrangian configuration description equal 0. And this animal is clearly nonlinear. And Piola didn't entitle his book, his article, his paper on non-linear equations for continuum mechanics because it was evident for him that the equations were nonlinear. So actually, one should not be surprised because the equations are nonlinear. One has to be surprised because the equations are linear. And actually, the equations are not linear. You are raping them and you are forcing them to be linear, making some assumptions simply because you want to try to solve them. Of course, when you linearize something, then you restrict the limit of possible applications of your equations. Okay, so this has to be clear. Now, I want to show you this with an example. My aim is to show you Lamé equation for linear isotropic elastic solids, and you will see it is even more trivial after all the work we have done, the Stokes-Navier equations for the dissipative part of Cauchy stress. Okay? And I want to show you that what we have done in the general setting easily produces the result which otherwise is nearly impossible to understand. So nobody will prove, nobody is able to prove for you directly which is the form of isotropic tensor functions of a tensor variable. The only thing which is possible is to prove which is the form of a non-linear isotropic equation, constitutive equation, and then what you have to do is to linearize them. So I remind you what we have written. We have written that an isotropic tensor function, so T a symmetric tensor, which is the image under an isotropic function of a symmetric tensor, can be expressed in this way. So, for what we have said, this is a non-linear function of the symmetric tensor variable E. It is already a lucky circumstance. Behind this, there is the Calais-Hamilton theorem, which I finally decided to skip, but I can tell you quickly what happens. If you write formally the secular equation for eigenvalues, and instead of the scalar quantity, you replace it in the secular equation, you replace the tensor itself, because you can calculate every power of a tensor, and the coefficient in the secular equation is a scalar. Okay, Calais-Hamilton theorem tells you that also the tensor itself verifies the secular equation, which means that E cube, if you have a 3 times 3 matrix, or a tensor defined in a 3-dimensional vector space, mapping it in another 3-dimensional vector space, the cube of this tensor can be represented as a function of the lower powers. Okay? So, actually, if you add here more terms, you can represent all higher order powers as a function of the lower order powers. However, somebody could say why an isotropic function should be polynomial in the variable E. Okay, so for this reason you need the theorem. Okay. However, V0, V1 and V2, of course here I have the invariance, they can be a generic function of the invariance. So you can have logarithm of the second invariant to the cube. I mean, you can have everything here. So it is polynomial only in terms of the powers of E as a tensor variable. These scalar quantities, they can be generic functions of the invariance. Okay. So I want, of course, E can be everything. I mean, E can be any tensorial quantity, and T can be any tensorial quantity, and this equality holds only under the assumption that the function T is isotropic. So you can apply in every context. Now let us zoom a little bit in continuum mechanics. So let us particularize in continuum mechanics, and let us go back to our standard picture. So you have reference configuration, the vectors in the reference configuration, actual configuration and vectors in actual configuration. So any vector small v index I in the actual configuration can be represented in terms, if you linearize chi, can be represented in terms of the gradient of chi applied to the vector which lives in the reference description. So this is a segment of material particles, and this one is a displacement which goes from the position occupied by the first material particle to the position occupied by the last material particle in that segment in linearized description. So when you consider a small volume in the reference configuration, then you can truncate the Taylor expansion and you can consider the Jacobian matrix of K, which we called F, in order to know what happens in the neighborhood of a material particle. So I want to underline that we are linearizing the function K in the neighborhood of a given point when we introduce F. So what happens? Somebody asked me, therefore, if you consider this measure of deformation, you are linearizing. So you are considering small deformations. And while giving my lectures, I called capital C as a finite deformation measure. So somebody could be puzzled by this. So you have to understand that this F transpose F is measuring the deformation of a small cube in the neighborhood of a point capital X. So we are considering something small. What we are considering small is the volume around a point X. Instead, you can consider small deformation by assuming that K of X is equal to capital X plus epsilon, a displacement U of X. And this displacement is small. This is another smallness. Whenever you neglect all powers of this epsilon greater than the first one, then you are considering small deformations. So you have two different independent things which are small. The volume around a given material particle and the displacement of the whole set of particles. Okay? So while in fluid mechanics you can always consider capital C to be meaningful in a sense, because once you have labeled a material particle of fluid, you can always decide to shrink the volume around it and to have it as small as you like. In fluid mechanics, generally, this U soon becomes very big and you are lost. You cannot linearize the equations in the Lagrangian configuration. This is the true reason for which solid mechanics and fluid mechanics are taught by different persons. Simply because the methods of solutions are different. But from the conceptual point of view, the two belong to a bigger theory which we could call continuum mechanics. Now, what we have to understand is what happens to this C when the displacement is small. Okay? Now, the first thing which happens is this one. The index I can be confused with the index capital A, or the Lagrangian indices can be confused with the Eulerian indices. This is what has to be understood, and it is not so easy to understand. You can embed the vector space in Lagrangian configuration, and the vector space tangent to every point in the Eulerian configuration, you can embed it in a unique vector space. So you can identify this vector and that vector as vectors of a third vector space. So what happens is that you can define a parallel transport of a vector from here to there. So you can introduce the delta AI VI equal VI, the parallel transport of a vector from referential description to Eulerian description. When you have a small deformation, you can neglect every difference between the vectors living here and the vectors living there, and this parallel transport is used for mixing the components. Now, if you look at this equation in components, you have this which is rather, I have even difficulties in writing this equality, because this animal lives here, while this is a vector field defined here, but having indices there. So to write this equality is very difficult unless you manage to use the same reference, the same basis, the same configuration, the orthogonal system or coordinate system for both Lagrangian and Eulerian description. And this can be done only if this is deformed a little bit to go in the deformed configuration. So these arrows, UI, can be represented in the vector space of the Lagrangian configuration. So you can mix the small index with the big index. So this difficulty will arise immediately. So I want to do some calculations for you so that you can understand why we are lost easily if we don't make the right reasoning. So CAB, which is the correct deformation measure, can be written as FIAFIB, okay, and F is delta IA. So I am introducing the identification of the here. If you write delta, you identify every vector in the Eulerian description with a vector in the Lagrangian description, and you say that the components are the same. Okay? With this, if you keep this careful choice, you can write this equation in this way. So here you have delta IA, delta IB. It is wonderful. The Levi-Civita trick gives you delta AB, which is the identity in the Lagrangian configuration, and you are happy. Okay? Then you have epsilon UI A delta IB. Okay? Then you have plus epsilon UIB delta IA, and then you have epsilon square, which you decide can be neglected. Now, if you identify once more the vector in one configuration and the same vector in the second configuration, then you have U B comma A and UA comma B, which is the symmetric times epsilon, which is 2 times the symmetric part of the displacement gradient. Okay? So actually you can say that when you can neglect infinitesimals of higher order, this animal is equal to delta AB plus 2 times the symmetric part. The symbol is this one, usually times epsilon. The symmetric part of a tensor having 2 indices is indicated with the brackets. This means exactly this. Okay?
So this means that, I mean, when you take the FIB,
yeah,
you are lowering the I index from the contravariance.
I mean, this is saturated here.
No, I mean, if you start from Fi contravariant, A contravariant,
yeah,
the first one, and you lower the I index,
yeah,
you get the guy with the 2 low indices, right?
yeah.
Then you need a metric tensor
Yeah.
doing this. So your metric tensor is this delta IB.
This delta IB.
Okay, so you are linearizing the metric tensor.
I am identifying, I mean, in this story there are 3 metric tensors. You have the metric tensor here, the metric tensor here, and the metric tensor here as induced by the deformation.
Yeah.
And I'm telling that the metric tensor induced by the deformation is equal to the identity plus this new tensor,
Okay.
with small deformations.
Yeah. No, I was considering the second equality of it. Yeah.
This one?
Yeah, the right part with the bracket, the circle bracket.
Yeah.
And you have delta IB.
Yes.
The first part, delta IB, right?
Yeah, this is not an inner product. This is this animal is a parallel transport.
But it's not I mean, when you are going to lower the F, the I index of the F,
Yes.
to get the FIB covariant.
Yes.
That FIB covariant is the bracket term there.
This is FIB.
Linearization of that, right?
Yeah. No, this is the exact expression because you assume that you have this exact equation.
Okay, but then when you are going to write the covariant component of X, starting from the contravariance,
Yes.
you need the metric tensor.
Yes.
So you're saying that
Okay. This is not the lowering inner product matrix. This is the parallel transport. Delta IB.
okay, this is clear, but look, I have delta IA.
Okay.
So to get delta IB covariant,
Yes.
lower the I index.
Yes. So you want to say that delta IB is equal to GIJ delta JB.
Perfect. Then the Gij should be a delta.
No, this Gij is the inner product here. This is the parallel transport, which transports contravariant vectors into covariant vectors parallel, and this animal is the parallel transport, which is transporting contravariant vectors into contravariant vectors. And this formula tells you how the two parallel transports are related one to the other. I mean, this is the wonderful vision of Levi-Civita, which allowed us to understand all this. So you can represent parallel transport in different ways. You can take a contravariant index and to parallel transport it into a covariant index.
Sure.
This is what we needed here.
Sure.
Then you can, otherwise you can transport a contravariant index into a contravariant index. Now the question is how they are related. The metric tensor is relating them. Actually, as you are provoking me, so I tell you this, there is a wonderful theorem. Given an inner product, there is a unique parallel transport. So once we have built this Riemannian structure, then there is a unique parallel transport which works.
Okay, so it's quite natural that Gij is delta Ij actually.
If you have chosen an orthonormal basis.
Yes, of course, yes. Which is what we always did.
Yeah. Right? I don't want, you know, what is dangerous is that if you declare that everything is orthonormal, then this equation becomes trivial. And you cannot interpret what is happening. So this is the big, if you are not careful enough to distinguish between contravariant and covariant vectors, and if you are not introducing parallel transport, these equations becomes a mess.
That is the metric tensor in a basis, and the scalar product is the Euclidean.
Yeah. Then I don't tell you which
base are you using?
Which base I'm using, so I cannot simplify this into delta Ij. Okay?
Okay, so just so a last comment.
Yeah.
So this means that the delta IB covariant,
Delta,
in general, that is not the connected delta.
the delta, this animal here is the inner product in AB. Because when you consider the identification,
But also the other one, the mixed one, the delta IB. On the second.
no, this one is always a parallel transport.
Yes, but that symbol is not the connected delta, the one which is one if the two indices are equal, or because that is the
This is a map which maps the component capital A contravariant in the component small I covariant. So in a sense it is an abuse of notation.
Yeah, the choice is okay.
Okay, but
Instead, if you are
okay, so
instead it will become
yes.
connected.
So this is the proof that this part of our discussion is a mess, because there are too many delicate ingredients. Okay. However, I believe. So I try to repeat so we see if we have found a common agreement. We are trying to identify the set of vectors in the Lagrangian configuration and the set of vectors in the Eulerian configuration. So the first choice is to decide to use the same, so 3 copies of the same basis. And I call delta IB the parallel transport, which takes a vector here and transports it there. And because of the position of the indices, this is mapping the contravariant components into covariant components. Of course, if this reference, this basis is orthonormal, for sure this animal is a Kronecker delta. Okay? But I want to call it in this way because then I need to saturate it. Okay, and I must distinguish between big capital indices and small indices. So at the end of this story, if I have a small displacement u, I discover that the green deformation measure, which is an inner product, is equal to the Lagrangian inner product, which is a standard delta inner product if we have chosen orthonormal system, plus 2 times epsilon, the symmetric, times epsilon times 2 times the symmetric part of u, which is a symmetric tensor. So in a sense, we are of course, this is not true exactly, because here you have plus epsilon square something, which we decide to neglect. Because we truncate every Taylor expansion in epsilon to the first order. So this is what we want to do. So linearization means you have a small parameter which has to be a scalar one, and you develop in Taylor's expansion everything, and you neglect everything which is of higher order than the first. So second and higher orders are neglected. So you find sometimes capital C equal to I plus epsilon capital E, where capital E is written grad U plus grad U transposed divided 2. I think that this expression is useful only if you have written it component-wise. So you know what is going to happen. Otherwise, you are in troubles. Okay. Now we are ready to do what I promised you 3 lectures ago. We have a solid. This solid is isotropic, and we want to discover which is the form of an isotropic constitutive equation for stress. Okay, so what I've done, I've done something. I have written Piola stress. Piola stress is this one, okay? But F is identity plus epsilon, okay? If we will go to linearize dW over dCRB, and this animal will be linear in epsilon, okay? Then you see that the structure of Piola stress will be dictated that the epsilon terms and all other terms will be killed. Okay, so we will go in this later, because this is a delicate point involving stress in the reference configuration. Something which you have to keep in mind is that 99% of times people are presenting equations in which in the reference configuration stress is 0. So in absence of displacement, when epsilon is equal to 0, Piola stress is vanishing. So we have to understand this more carefully, but I prefer to start with an easy Taylor expansion so you understand what is going on. Okay, so we can decide to write stress as a function of C, okay, and we can try to check what happens in the neighborhood of C equal 1. So what we want to do, we want to replace T of C and this animal can be Piola stress, for instance. And we want to linearize this expression. So we want to discover what happens to this expression when you can neglect all terms of order higher than epsilon. So you want to get this as a function of epsilon E, linear, because C minus I equal epsilon E. This is what we want to do. Of course, when C is the identity, this equation tells you that in general T of identity is equal to something times the identity. Okay? So we can tell this, the stress in the reference configuration for an isotropic solid has to be spherical. By the way, this is not so easy to prove directly, but this formula tells you this. But we will do more. We assume that this is equal to 0. So no stress in the reference configuration. So in the Taylor expansion, you get something times epsilon E. And we have to discover how this something looks like. Okay? What we do? We develop everything on the right side in Taylor expansion, which is not so easy and you find very confusing stuff. So let us try to do things with a certain order. Okay? Okay. So we want to write T of C as T of I, identity, 1, plus dt over T, dt over dc, C equal identity, times C minus E plus infinitesimals. Okay? And this C minus I we have called epsilon E, and we have discovered it is the symmetric part of grad U. Okay? I believe that I said this in a clear, ordered way. Okay? In general, these things are kept not said. Okay? Okay, so I tried to say it in the right way. So now I need to calculate dt over dc. And then I need to calculate this with c equal I. And I will get this coefficient. Okay? Now, at the end of the story, we discovered that all this can be written. This is what we will prove. Lambda times E plus, mu E plus 2 lambda trace of E identity, where mu and lambda are some constants. Okay? So the whole this animal is written in this way. Okay? So actually, to get this, dt over dc, I try c equal identity, is equal to mu Now we are facing a serious problem. We need a linear map which maps tensors into tensors. So I was preparing this for showing you the whole difficulty. So here I need something which is a fourth order tensor which maps a second order tensor into a second order tensor. Okay, but this is the identity, because it has to take epsilon, and to this epsilon it has to associate E itself. Okay. While we need another stuff here which takes 2 lambda. This I can write more easily. You have the identity, okay, and then you need to take something, again the identity, apply inner product to E, and this animal we check is equal to the trace of E. Okay? So we are facing this problem. We need to understand what happens to this equation when linearizing. Okay? So, and this is the difficulty which we need to face now. It is not possible in half an hour or something more to do everything which I'm telling you in a clear way. So let us try to give you the main ideas. First thing, I need a fourth order tensor which is called linear elasticity tensor, which maps the capital E deformation measure into the corresponding stress. Now, the statement by Calais is that with only two numbers, you can construct this capital C for isotropic materials. This is the first statement. Another statement is this one. How many sees independent you have for the most generic solid. Okay? So I want, it is stronger than me, I want to tell you that you have exactly 21 of them. So in order to characterize the most general linear elastic material, you need 21 coefficients. Now, it is very easy with what we have said up to now to discover this number. So the reasoning takes some minutes. We try to understand it quickly because to characterize an isotropic material, you need only two measurements. You take a cylinder, you press it with a free lateral mantle, so you have a not constrained measurement, and you measure elongation as a function of applied force. Then you consider a much more rigid lateral wall. I mean, you need to embed this cylinder in a hole in which built in a material which is much more rigid than the material you are studying, so that you can tell that the lateral wall will not move, so you have a constrained measure, and you do the same stress-strain measurement. And in this way you measure the two coefficients of an isotropic material. Nobody knows which protocol has to be used in order to characterize all 21 parameters which are needed for characterizing a linear elastic material. So, in my opinion, one has to know that there are 21 parameters. So if somebody gives you a piece of a material, in general, you must be ready to find in linear elasticity 21 numbers. Why I'm telling you this? If you blindly apply the procedure for measuring the two Lamé coefficients, or equivalently the two Young and Poisson moduli, which are 1-to-1 corresponding to Lamé coefficients, using the standard procedure, you may discover that Poisson parameter is minus 20. While the first principle of thermodynamics tells you that this has to be between minus 1/2 up to 1. What is happening? The material is not isotropic. So you believe that you are measuring Poisson modulus. Actually, you are measuring a mixture of moduli, and you do not know what you are doing. You know, I've seen a certificate signed by a full professor from an important university in Italy at the bottom of a document in which Poisson modulus measured was minus 3. So it is stronger than me. I need to tell you that there are 21 parameters. Okay, now let us calculate. In general, I, J, K, H can vary assuming 3 values. So you have 3 times 3, 9 times 9, 81. However, this map is a map from symmetric into symmetric tensors. So actually, this is another information you need to know. In a symmetric matrix, you have 3 independent coefficients. Okay? 6. Okay? Using Voigt choice, but you can use another one, you can transform this matrix into a column of 6 components. This is very dangerous. Sometimes it is very useful, but this is very dangerous. Because once you have placed them in a column, you lose the possibility of multiply it times Q and Q transposed and to check what happens with a change of observer. So the tensorial nature of this animal is lost. If you call this if you call E1 equal, if you write E1 equal E11, E2 equal E22, and so on, and you transform an animal with 2 indices in an animal with 1 index, you have lost all possibility of checking contravariance and covariance under the change of observer. So it can be very useful to do some calculations, but it is deadly for understanding what is going on. Okay? However, in our reasoning, this reordering is very useful. Why? Because you immediately discover that you have 6 times 6, 36 components of C, simply because you have that this animal is symmetric and this animal is symmetric. However, we are starting with an energy. And if you remember, I have erased the formula. Piola stress is related to the derivative of the energy. In order to get a linear stress-strain relationship, you need a quadratic energy. Okay? In order to get a quadratic energy, you need a quadratic form. And this quadratic form, in absence of stress in the reference configuration, is homogeneous quadratic. Okay, so you have a quadratic polynomial in E without the linear term. And this quadratic polynomial gives you the energy W of E equal 1/2 E ij C ij hk E hk. This is the quadratic form of energy. So, not only the symmetry with respect to this first and second and third and fourth index has to be valid, but also the change. So Cij hk has to be equal to Chk ij. Okay? Now you can get the same result with a much more painful procedure. There are books in which, in order to avoid to talk about least action principle, they accept to arrive here and then to spend 10 pages for telling you that take an infinitesimal volume of solid linear elastic material and consider any cyclic deformation of this animal, and for every cycle which starts from a deformation and comes back to this deformation, the total exchange energy is 0, and from that they deduce this symmetry. So So in order not to say that equilibrium is minimum of energy, they prefer to introduce at the end of the story the first principle of thermodynamics, which, by the way, is equivalent to the fact that you have the equilibrium with a minimum of total energy. Okay? In a much more complicated way. Now, if you accept there is a deformation energy, once you have accepted the linear relationship between stress and strain, and in absence of stress in reference configuration, you are sure that your energy is quadratic. Okay? So, in Voigt representation, you have 6 components of deformation, 6 components of stress, and you have a 6 times 6 matrix, which gives you the elasticity matrix. How many elements you have in the diagonal? 6. This matrix is symmetric. Okay, we have said now. So 36 minus 6 divided 2 is 15. The coefficients on this side are 15 plus 6, 21. So in order to characterize a linear elastic solid, you need 21 elasticity moduli, which is the simplest linear elastic solid, an isotropic solid. Okay, so let us go back to our brutal expansion. Every term here has to be reduced into a linear expression in terms of C minus identity. Okay? So, let us take this term. This term is identity. Then you have V0 of the invariance of 1 plus epsilon V0 calculated in dV0 over the invariance of C, calculated in C equal to 1, okay? And here you have to consider what? The invariant of epsilon, the first invariant of epsilon, the second invariant of epsilon, the third invariant of epsilon. Okay? So this is dV0 on the first invariant, dV0 on the second invariant, dV0 in the third invariant, calculated in C equal the identity, and then you have to estimate the first, the second, and the third invariant of E. However, here you need to consider only the linear part of it. Okay? So you understand what we need to do. We need to consider the Taylor expansion of every invariant and to truncate it at the first order. Here, either you consider identity and you do the same as before, or you consider this constant and you consider here E. Okay? So this animal reduces to this analysis. Here, either you consider this is identity only, because otherwise you have epsilon squared and it is killed. Okay? Okay. This is the reason for which now I start calculating. Maybe I will give you some results. I need to start calculating the derivatives. The derivative of the first invariant of a given matrix G with respect to GAB. Okay. This we can do quickly. What is the first invariant of G? Is G11, G22 plus G33. So this derivative is 1, 1, 1, 0, 0, 0. So this is delta. This is a horrible abuse of notation, but okay. I'm writing a matrix equal something. Maybe I should write this way for telling this matrix is equal to this matrix, which is equal to this matrix. Okay? So, this derivative is actually the identity. Okay? So, when you consider this animal here, the trace of E, in linearized terms, okay, you get simply epsilon trace of E, and nothing happens. So you discover that one ingredient in your expression is trace of E. Okay? So at the end of the story, you are building this animal in your linear representation. Okay. Do you remember we have already calculated the determinant of F with respect to F, where F is a generic matrix? So even if this means to rush a little bit, the third invariant of a matrix G is equal to, if this G, so you have G equal identity plus epsilon something. Okay? If you consider the Taylor expansion, you use that the derivative of the determinant of a matrix with respect to the matrix in the neighborhood is determinant F minus transposed. Okay, you remember this formula we have proven many times. So the determinant of F over dF is equal to determinant of F times to F minus transposed. Okay, you calculate this in the identity, and then you consider, so the trace of G is equal, the determinant of G is the determinant of identity, plus this derivative calculated in the identity times the increment, okay? You discover that this is 1 plus epsilon trace of G. This is already something which you read everywhere. Usually in the books of solid mechanics, they introduce the volumic change between the passage, in the passage between reference to actual configuration only in linearized terms. So it becomes very painful to study large deformations because they must start everything from the very beginning. This is true only when you can neglect higher order in epsilon. Okay? So once more, when considering the development of this animal, you get trace. So you can gather all coefficients. So you have built the parts of 2 lambda appearing here. Now, what is very strange, I couldn't find, so I did the calculations, I couldn't find the derivative of the second invariant with respect to a matrix. This will produce another term in trace, but also this E. So, the derivative of the second invariant of G with respect to GAB. By the way, this term comes also from the linear term in the general theorem we have proven, assuming constant V1. You remember, we have V1 invariance of E times E in the isotropy representation. So if this is constant and this is varying with epsilon, you get already a term like that. Okay? So the invariant of G over dG is the derivative of trace of G square over dGAB, and I will not bore you with this term because this is 2 trace of G times d trace of G over dGAB, and we have already treated it. Okay? So this gives you another term similar to the one we already got. So we write a symbol here for meaning that we are getting, it's not equal anymore. Okay? And then you have the trace of G square over the GAB. Okay? Now, this we can write in this way. So I'm using the chain rule. This animal we already calculated, and so this is the identity. So this is delta DL. Okay, because you have G square with respect to the component of G square. Okay, so this you can write delta DL. This animal we calculate here on the side. So I agree with you that in this part I'm doing calculation quickly, but I'm giving you all details needed for completing everything by yourself. So the idea is that you should try to reproduce slowly, you need half a day, these calculations by yourself. Now the trick here is this derivative, but this derivative is very easy because look, the G square DL over the GAB, this is equal. Now, what is G square DL? Is the component DL of the square of G. So this animal is G D M G M L. G is symmetric, so I should not worry about the order. This is DL, and I have a sum over M, so I write it this way. Okay, so I need to calculate the derivative of this animal with respect to G A B. Okay, this is easy. This is 2 times sum over M of G D. Okay, this better we do this way. So it is sum over M. Okay, when doing these calculations, I am a bad boy. I'm using all the time, it is symmetric, so I'm jumping a lot of passages. Okay, so this is after considering the symmetry of these 2 animals. This is equal to 2 sum over M of D G dm over the GAB GML, okay, so plus the other one on the other side, okay, but this animal is symmetric, so I can place 2 times. This derivative we did many times. This is delta dA delta MB. So at the end of the story, I write you the final result. I could be wrong with some, but I don't think so. dG square CD equal dGAB is equal to 2 times delta AC, okay, delta AC GBD plus delta AD GBC, okay? So at the end, you are left with another animal which produces either E or trace of E. So actually, even if the Lamé formula is very easy to write down, it is the final result of a very complex process. And the very complex process involves, I repeat what we have done. You have that Piola and Cauchy stress, which in linearized elasticity with 0 stress coincide, which is equal to, in general, to this expression invariance, of course. Okay? Then you linearize this animal, and at the end, as the third invariant is nearly equal in linearized theory to the trace 1 plus epsilon trace, and as the second invariant can be expressed in terms of the trace and of C, at the end of the story, this reduces to lambda trace of E identity. Okay, I mean, this is an expression then I want to write this C, and this is nearly equal to T of 1 plus something, where E is C minus identity, okay? This is, in our reasoning, 0. It can be studied, but never try to build this for isotropic materials to be non-spherical, because it has to be spherical, okay? You get lambda trace of E identity plus 2 mu E, and that's it, okay? Don't ask me why, there is a reason, and I'm always placing the 2 in the wrong side, but I think this is the right position. This is historical, because the first moduli which were introduced are not this one, are Young moduli and Poisson moduli. So this 2 simplifies the expression of the old one in terms of new ones. So at the end of the story, you get this animal. Now, are we using in a way that T means Piola stress and C means deformation measure? We never used it. We have only used that C is symmetric, T is symmetric, and the dependence is isotropic. So, if instead of being interested in the dependence of Piola stress in the deformation measure, the dependence of Piola stress on deformation measure, you are interested in the dependence of Navier-Stokes dissipative part of stress as a function of the symmetric part of the gradient of velocity, for non-linear viscosities, you get this general representation. Okay? If your velocity field is small and close to a constant velocity field, then you can linearize everything and you get this expression. Now, I know somebody that told me, this is wrong. Here you should have divergence. But D11 is equal to V1, comma 1. D22 is, so this is the divergence of V. Okay, and this is the symmetric part of the gradient of velocity. So the true theoretical basis of both representation is the same. However, while this isotropy is unavoidable, because isotropy here means that the dissipation in dissipative Navier-Stokes flow is independent of the observer, which is a rather universal requirement. The corresponding equation, which I wrote before, is valid only for isotropic solids, not for all solids. So, the two Lamé coefficients are two particular moduli for linear elasticity. The most general linear elasticity requires 21 coefficients. The two mu and lambdas which you need in Navier-Stokes flow, they are the most general linear dissipation moduli. In order to get more moduli, you must go up and write second order. So you need to introduce a stress dissipative stress which does not depend linearly on D, but depends quadratically, maybe. But it is always isotropic, because the requirement of invariance under change of observer is still valid. So this is a true difference between the two things. Okay, so I want to apologize another time about the fact that in the last part I rushed. Okay, but actually I was calculating a Taylor expansion truncated at the first order. So you can reconstruct this. It is not so difficult. The main idea I wanted to communicate to you, I believe I communicated. The main idea is that we have a general theorem for isotropic functions whose independent variable is a symmetric tensor and whose dependent variable is another symmetric tensor. These isotropic functions have this form, and these functions play an important role in solid mechanics and fluid mechanics. In solid mechanics, you characterize isotropic solids, linear elastic solids, or in general, isotropic non-linear elastic solids. In fluid mechanics, you characterize Navier-Stokes dissipative fluids. Okay? Okay, so I think that's it.